Too much? Yeah, same. Wow. I know, right? I know. I was like, she's cool. Yeah, so like my friend had it's like in the middle of the night. So that like, oh, the latest weekend. Oh no, it's just those things that we do. Oh, yeah.
Yeah, the class starts at 4.
It's 5. Oh, we gotta go.
You guys can do it. Do it 5 minutes. Do you guys need to go somewhere?
Yeah, it's the next room.
You said it.
How many questions are in the midterm? Yeah, there's going to be 10 conceptual questions and 1 question where you're going to be asked to derive the equations for an LPN. Hey, how's it going?
Good, how are you?
Good, good. Yeah. So you can definitely expect it to be similar to the homework. And so there will be short answer questions, very similar to the homeworks, and the LPN problem will be very similar to the homework as well. Yep. Okay, it's 4 o'clock, so let's go and get started today. So we got a busy day today, and so we're going to be learning SimVascular today and talk about the final project and doing a lot of stuff. So you know, it's going to be fun. All right, so how's everyone doing today? Doing good, doing good. Okay. We're the end of week 13 now, and so after this we have 3 more weeks, and so one of those days we're going to take a midterm. Oh, I forgot to tell you guys. So I did get a guest speaker. So she's a good friend of mine from grad school. So she's going to come in on the very last week to talk about her work on the FDA. So that's exciting news for this class as well. Okay. All right. And so today we're going to do we're going to talk about you know, the additional requirements for the final project. I say that, you know, because it's basically just a continuation of your midterm project. And then we're going to learn how to do simulations in SimVascular. Okay? And so today, you know, before I really get started today, you can kind of do today in 2 different ways. And so, well, I guess 3. And so the third option is just to kind of sit there and listen, which is fine too. But if you want to follow along, you know, you can either, oh, I forgot to post the lecture from Tuesday. If you want to follow along, what you can do is you can use your midterm project. And so if you have that on you right now, and then you can go through the process of smoothing, meshing, and preparing the simulation files. And if you want to do that, that's great. Then you're going to be, you know, in great shape for the final project. Then all you have to do is just run the simulation and analyze the results and write the report. Okay. Or if you want to follow along exactly what I'm doing in terms of the numbers, in terms of what the model looks like, I've uploaded kind of a completed version of the tutorial project here. Okay. And so if you go to the course website on week 13, you can click on demoproject.zip. And that's going to be like a completed SimVascular tutorial. Okay. And so if you want to kind of follow along exactly with what I'm doing, you can do that. Or you can just do today with your midterm project and kind of be a step ahead. Okay. You'll be pleasantly surprised to know that, you know, I would say probably the most time-consuming part of the SimVascular modeling is already done, and so, you know, building the geometric model is you know, definitely a lot more time-consuming. And assuming that you've built a good model, you know, running the simulation is very you know, it takes a while, but then you don't have to be there for all of it. And so, you know, I think this is kind of a good time. Because I know at this point in the semester, I know a lot of you are seniors or graduating or you're grad students. You guys are really busy, And so I wanted to get the model building out of the way first, and then so that this part of the project is a little bit lighter on that stuff. Okay. Okay, and so that's it for my announcements. And so are there any questions I can answer before we get started today? Okay, all right, so let me first start talking about the specifications for the final project, okay? And so like I mentioned, the final project is basically just a continuation of what you've done already for the midterm project, okay? And so far, you've built a patient-specific model, and so, here's one, okay? So yours looks different because you have a different patient. And what you have to do from here is that you're gonna have to run a CFD simulation on it. You're going to have to analyze the results, look at things like the pressures and the wall shear stresses and the velocities, and then you're going to write a report that summarizes your findings. Okay. Okay. And so a big part of these specifications are a little bit repeat of what we're going to go over today. And so they talk a little bit about how you're going to set up the simulation, the steps that are involved. Okay. And so I'm not going to go over that in detail today, but what I do want to go over is kind of the requirements for the, for the report. Okay. Okay, and so you'll see after you run your simulation, you're gonna get simulation results, right? And the simulation results, the way that they're going to, the form that they're going to take, is you're going to basically be, it's going to be like this, right? And so you're going to have your three-dimensional model, and you're going to be able to see what the pressures look like, what the wall shear stresses look like, and what the, what all the velocity patterns look like in the model. Okay. And then from those results, you should be able to draw a lot of interesting conclusions about your patient. Okay? Because all of you have chosen a model of a specific part of the body. And so a lot of you have done aorta, a lot of you have done pulmonaries, right? And there's different kinds of fluid mechanical quantities that are of interest in those different parts of the body. Okay. Some of you actually might in fact be modeling a disease state, which is even more interesting because then you'll have a lot to really talk about. Okay. Okay. And so part of this final project is that it's more than just kind of running a simulation and just putting some pretty pictures into a document. I want you to do a little bit of research in terms of what is the part of the body that you're looking at, or maybe what is the disease that you're looking at, and what are the relevant fluid mechanical quantities that lead to that disease. Okay. And then write about that in your report, right? And so, this section of the specifications right here will describe to you, what kinds of results that you should put in, and what kinds of questions that you should answer about those results. Okay. And so, first of all, the first result field that I want you to display is the pressure. Okay. And so the pressure field is basically a spatial distribution of what the pressure is inside your patient-specific model. Okay. And to help you analyze the pressure field, I've come up with 3 discussion questions here that you can answer in your report. Okay. And so first of all, I just want you to describe in words, what the pressure distribution looks like in your patient. Okay. And what you should see actually is something that looks like this image here. Okay. And so generally speaking, what you should see is that there should be a gradient. Okay. And so you should have higher pressures near your inlets. And so for this particular model, this one's unique in that it has 3 different inlets. And so this is an inlet. This is an inlet, and this is an inlet, okay? And so at all of these faces, blood is coming into the model. Okay. Okay. And then it's flowing through through all the branches and coming out at all the outlet caps, okay? And so generally what you should see for the pressure is that you should have higher pressures at the inlet and lower pressures at the outlet. And so that's kind of the first thing that you should check. And that's always kind of a good first sanity check to make sure that your simulation ran properly. Okay. Okay, so that's the pressure field. Okay, so I want you to describe what it looks like and just check to make sure that you have that high to low pattern. Okay. Next, I want you to say, based on the pressure distribution, what can you say about the health of this patient? Okay. And so does this patient have high blood pressure? Do they have areas where the pressure drop is significant? Okay. And so that question there is pretty broad. And so you're gonna have to do a bit of research on your own in terms of, what are some typical values of pressure in these types of anatomies, and how does your simulation relate to those pressures? Okay. And number 3, this might not apply to everyone, but if you have a region in your model where you have a narrowing in your model, and so there might be some kind of disease or something, then what you might see is that there might be an area where the pressure drops pretty significantly. Okay. And so it goes from an area of high pressure to low pressure. And actually, I chose this image here to kind of show you exactly that. And so if you look at this region of the model right here, okay, right? And so we know the blood is kind of flowing through this model in this direction. And so as the blood kind of crosses from this big branch to this small blue daughter artery, right? We see a pretty big drop in pressure, right? And so we go from a red pressure, which indicates a fairly high pressure, to something that's blue, which indicates low, right? And so you have a pretty big drop in such a short amount of time. Usually, when that occurs, that means that there's some kind of disease occurring at that time. Okay. And so I want you to look out for these kinds of areas in your model to try to comment on, is there any kind of risk for disease here, or is there any kind of bad bad flow quantities there? Okay. All these things that you would talk about just from the pressure. Okay. All right. Any questions on this so far? Okay. Yep.
So that could be so that high result being bad is maybe just like
yeah, no, I know what you mean. So yeah, there definitely can still be there can definitely be issues with the simulation. And that's something that, if you do see something like this, we can talk about it and see, because there's ways to set up the simulation where something like this can occur, but it doesn't necessarily mean that there's a disease there. And so, that you're going to have to kind of, talk about it with me. And so I will say that I don't think many of your models have that. And so I think most of your models, you should see a fairly smooth distribution pressure. But it can happen. And so, I just want you guys to be aware of it. And if it does happen, then, it could be that there's disease there. Okay. Yep. Mm-hmm. Okay, so that's the pressure. And so the next field that you're going to be able to see is the wall shear stress, right? So we've talked about the wall shear stress quite a bit in this class, and both in terms of, what it is and what it can be used for. And so I want you to, display the wall shear stress in your report, and also just spend a little time talking about it, right? So first of all, describe just what the wall shear stress distribution looks like, right? I want you to look and see, where the wall shear stresses are really high and where they're really low, okay? And number two, we spent quite a bit of time earlier in the semester talking about Murray's law, right? And so Murray's law basically says that, when you go from a higher, a parent vessel and it bifurcates to a smaller one, then the wall shear stress value should be roughly the same, okay? And so, in theory, you should be able to see that in your models as well, based on the size of the daughter vessels relative to the parents, okay? And so, I want you guys to look out for that and see if you can observe the same thing. Okay, and so the third main result I want you to show are the streamlines. And actually, I have it's not here, but I gave a presentation earlier this week showing that. Right, so the velocity streamlines, what they are basically they basically trace out the path of the blood as it flows through your model. Okay. And so you can get really cool animations like this, where all these little strings here, they look like hair, or they look like spaghetti, right? So those you can think of those as like the paths that the blood is flowing, right? So the blood is flowing from the top here and it's going down. And so you can make an animation like this to kind of show, which direction that they're going and everything like that. Okay? So this model here is a little bit kind of boring actually, because it's just a tube, and so the flow is just going straight through. But if your model has something like an aneurysm, or maybe it has some place where the flow is recirculating, then you can see that in the velocity streamlines. And depending on your disease, depending on the model that you chose, you might see streamlines that might circulate in something like this, right? As you might see like vortices form, you might see like a recirculation zone. Okay? And that's really significant because those flow patterns are often precursors to disease. Okay, and so today, I'll show you how to form these so that you can view them in your projects. Okay, and I have some questions here that you can answer with regards to those velocity streamlines. Okay, so first of all, I want you to just describe what they look like. Okay, next I want you to take note of the areas in the model where you see a high amount of velocity. And so that's basically where the blood is flowing really fast, okay? And then I want you to compare that to, the previous figure, where, you noted where the high values of wall shear stress are, okay? And I want you to draw correlations between them. And so do you see a correlation between areas where the velocity is high and the wall shear stress is high, okay? And so if you do, I want you to comment that, make note of that. And it kind of explain why you think that's the case, okay? And number 3 here, I want you to also correlate, what are the areas of high velocity compared to the areas of high pressure drop, okay? And so you may or may not see a correlation for that as well. And so, I want you to take note of that and then make some comments on that as well, okay? And so the last requirement for the report is I want you to include one other figure, okay? And so because everyone's projects are pretty unique in terms of, what you're looking for in the simulation, there are some results that may make more sense for you than for others, okay? And so, this figure, I'm going to leave it up to you to have you decide, what's the most significant thing to show. But it could just be as simple as, one of the other results here, but just kind of zoomed in on a particular area, okay? Because I would say for a lot of your models, you built this entire, cardiovascular model, but there might just be a singular area or a small area of it where, the results are significant or of interest. And so if you just zoom in on that area and show me the pressure or show me the streamlines there, that constitutes that extra figure. Okay, so I want you to kind of think about, what makes sense as the extra figure, and then show that in your report. Okay. Okay. And so here's the bonus part. And so it's bonus, but if you're a grad student, it's not bonus, it's required. And so if you're taking this class for graduate credit, part of our university requirements, because this is a 400 level class, you have to do one extra assignment compared to the undergrads. And so the extra part of this is that you have to perform a literature review. Okay. So I've already talked to a couple of the grad students about this, but basically I want you to look into the literature and find a scientific paper based around computational cardiovascular simulations, and then just write me a summary. Okay, so fairly straightforward. So not the worst thing in the world. Okay, and so with that, I want to talk about the final report, okay? Because this is I would say, more so than the simulation. This is probably going to be what you're going to be graded on more, for your final project. Okay. And so, this class is an elective class, right? And so you're not really required to take it. And so, I want you to write this final report from the perspective of, you want to share kind of what you've learned in this class to, your peers, okay? And so you should kind of write your final report from an educational point of view, right? To kind of instruct them not only on, what your model is and what your specific disease is, but also just kind of the general methods of the class, okay? And because I think that's always nice, right? Because you can take this report and share it with your friends. Okay? Or more importantly, you could take this report and share it as part of a job interview. Okay, so you put it into like a auxiliary files, right? Because I guarantee you, probably the person that's going to be interviewing you for your job, they probably not aware of this, but of this technology, but they do have, you can expect that your audience has some reasonable technical knowledge, and so kind of write your report from the perspective of trying to teach people about this class. Okay. All right, and so I'll put out a template for the final report later, but basically these are the components that you have to have. So first of all, you have to have an abstract. And so the abstract is basically just a very brief summary of what the report is about. Okay. Number 2, you have to have an introduction and a background. Okay. And so I want you to talk about, first of all, introduce, what part of the body that you're simulating with your final report, but also, what are some diseases or what are some quantities that are particularly relevant. Okay. So that includes, where the vessels are located in the body, what function do they serve, what are the size of the vessels, typical values of flow and pressure, common diseases, and et cetera. Okay, so any information that you can find on this part of the body can be talked about here. Okay. Okay. And also, it's here. It's talked about here too. I want you to also describe, what computations we'll be able to analyze about this anatomy and what you hope to gain from the study. Right. Remember, we talked about on Tuesday. When you're running a CFD, you have to have an idea of what kind of information you want to get from the simulation. And so I want you to talk about that here in the introduction. Okay. All right, number 3. So number 3, you've already done it, and so number 3 is with regards to the geometric modeling mesh. Okay, but that part is as big a part of your final project as any. And so I want you to go into detail about the geometric modeling and the meshing. Okay, and so just very quickly, you should describe what are some of the overall geometric features, like how many inlets and outlets it has. What are the general size of the vessels. Okay. And then I want you to just walk me through your process. And so, what process did you go through to make the model? Okay. And so, I'll say that everyone in this class knows the process that you went through. So everyone in this class knows that you loaded image data, you made the centerline paths, you made the segmentations, you lofted it all. Okay. Maybe cried a couple times along the way when SimVascular crashed. Right. But I want you to describe that here in the report. Okay. Because remember, the person reading your report, you have to assume that they're not familiar with SimVascular and they're not familiar with this modeling process. Okay, and so I want you to talk about that in this report. Okay, and I want you to show these things as well. So I want you to show all the path lines in your model. I want you to show all the segmentations, as well as your final completed geometry. Okay. Okay, and section 4 is going to be your results and discussion. And so we already talked about that. And so we talked about the figures that you have to include and kind of the questions you have to answer. And so this is just kind of repeating the same thing. And then section 5 is your conclusion, of course. Okay. Okay. And so this is a bit redundant. So, there's no teams for this project, so it's all individual. But that said, it is usually productive to work together with your classmates, especially if you're having issues with the simulations. Okay. Okay. And so, as always, don't hesitate to reach out. I'm here to help you out, because I know for a lot of you, this is going to be your first time running a CFD. It's going to be your first time using a cluster. And so, there's a lot of new things that's going to be introduced in this project. And so if you're having trouble with any of it, or if you're confused about any of it, please don't hesitate to reach out, and, I'll be here to help you out as best I can. Okay. Okay. And so that's the final project specifications. And so you can find this document on Canvas. Okay. And so you can read through it yourself. And so within sometime next week, when I'm a little bit less busy, I'll post up the rubric that I'm going to use for the final project, as well as the template for your final report. All right, any questions on the final project? Okay. And just like we talked about before, the final project is due on Monday, May 23rd. So this is the Monday after finals week, but it's also the day of graduation. Okay. All right, so that's it for the final project. And so now let's go ahead and move on to SimVascular. Okay. And so before we start, actually, and so in case you haven't done it yet, you're going to need to download the flow solver onto your computer. Okay. And so some of you might have done this already, but if you go to simvascular.org and you go to download, okay, so you go click on download installation package, it's going to take you to SimTK. Right, you're going to have to download SVSolver right here. And so you haven't done this yet, you should definitely do it. You don't really need it until the very end today, but you will eventually need it. Okay. And so if you're running Windows like me, then it's they haven't released a Windows version in a while. And so I think I had to go all the way back to January of 2019 to get a Windows version. Okay. And so don't worry about it if you're running an old version. This code literally has not changed since 1977. And so I don't even know why they're putting out new versions of it. Maybe they're adding funny comments to it. Okay. All right. And so if you haven't done that yet, you should definitely do that. But we're not going to need it to the end. Okay. All right. And so finally, we are in SimVascular, right? And so like I mentioned earlier today, the purpose of today is to show you the process of how you actually set up a simulation. Okay. We talked about those general steps on Tuesday, but today you actually get to see them in practice in the software. All right, so first thing I'm going to do, I'm going to go ahead and open up a project. And so I'm going to open up the demo project. And so this is the one that's directly uploaded onto Canvas. Okay. Okay. And so the nice thing about this model is that the model itself is fairly clean. And so, we shouldn't have any issues with with everything. Okay. Okay, and so here is the model that we're working with. And so this is the tutorial model without the extra vessel. And so everyone here, modeled an extra one. And so this just has the aorta and just the iliac artery. Okay. All right. And so the first thing we're actually going to do is we're actually going to perform some smoothing on this model. Okay. And so it's kind of nice here that they made it into different colors. Okay. Because what can happen sometimes, and maybe this view is a little bit easier to see. Actually, this model is really clean already. Let me make a new one. Okay. Because what can happen is that you might have some rough features or some rough geometrical features on the outside of your model. Okay. All right, so let me create a new one just that you can kind of see what I mean. Okay, so here's a good example. Okay, and so if you look at kind of the intersection between these two, so for the most part, this model is actually pretty clean. So there's not much we need to clean up. But if you kind of look at the intersection between the two daughter vessels, right, we kind of have a sharp change. Okay? And so if you kind of look at this model is so clean. If you kind of look at this part right here, okay, you kind of have a sharp angle right here. So if you kind of draw the the surface contours, we kind of come in at kind of a very sharp angle right here. We have a sharp change of direction. Okay? And so for a lot of your models, depending on your segmentations, you might also have some rough parts of your model as well. Okay, that's totally fine. I mean, that's all part of the process. But what can happen sometimes is that when your model surface is a little bit rough, it might make it a little bit challenging to mesh, and your mesher might fail. Okay. And so before you mesh, it's usually a good idea to kind of smooth over your surface a bit so that it gives the mesher an easier time. Okay. And so that's the first thing we're going to do today. And so in order to perform smoothing, the way you're going to do it is you're going to select all the wall surfaces of your model. Okay. And so if you look at the model, if you look at the face list on the right, you should see your list of walls and caps. I want you to select all the walls. Okay, so you might have to hold Shift on your keyboard or hold Control to make sure you're selecting all of them at the same time. Okay. And the reason we're only smoothing the walls is that we usually don't want to touch the caps, because the caps are where we're going to apply the inlet and outlet boundary conditions, and so we want to make sure that those are preserved. Okay. The only thing that we want to smooth here are just rough sections on the wall and any kind of rough bifurcations that result from daughter vessels. Okay. All right, and so with both of the walls highlighted, you're going to go to the right here. And so on the bottom right of the screen, you should see a list of operations that you can do. Okay, so you should see global ops, local ops, trim, and extract center lines. Okay? And so where we want to go is we actually want to go to local ops. Okay. And so when you click local ops, you should see a few options here that show up. Okay? And so you're going to see an option here called decimation. We're going to have an option called Laplace smooth. Okay. We have an option called constraint smooth or CSTR smooth. We have linear subdivision and loop subdivision. Okay. All right. And so all of these options here, they're basically different options for you to kind of clean up the surface of your model. Okay. But the one that I like to use the most, just because it's the most stable, is the CSTR smooth. Okay. And so you're going to click on CSTR smooth. And then after you click on that, all you have to do is just click this button called Smooth Local. Okay, so there's some parameters that are associated with constraint smooth, but for the most part, you don't have to worry about them. Okay, so I'm just going to go ahead and click on Smooth Local. And actually, let me zoom in here so that you can kind of see. Okay. Actually, let me go Control Z. Okay, so I want you to kind of pay attention to see what's happening at this intersection right here, right? So right now we kind of have this almost like a sharp change in between those two vessels. Okay. And so watch what happens when I click Smooth Local. So it happens a little bit fast, and so don't blink. Okay. All right, and so you can see after we click Smooth Local, it kind of filled in this space a little bit, right? So it's not the cleanest right now, right? And so this is kind of just a first pass, but what it's attempting to do is that it's kind of attempting to smooth out this transition as much as possible. Okay. And so what you can do from here is you can click on Smooth Local a few times. Okay. And each time that you do it, it's going to smooth this out even more. Okay, so if I click this on, usually I like to do this maybe 3 or 4 times, okay, to kind of smooth out all the kinks in the surface, before we go to meshing. Okay, because after a certain point, it's not going to do anything more, and I think we're reaching that point now. Okay. Okay. But what that's done is that it's basically kind of lowered the angle here. Okay, and so it's made this transition between vessels a lot smoother. So that the meshing kind of has an easier time. Okay, so for those of you following along, was the smoothing kind of make sense of the surface here? Yeah.
So if you have like a bunch of walls you want us to go like one by one? Or
No, so you can just select all of them at once. Yeah, so just select all the walls at once. And so, yeah, some of you might have, a few, like a dozen walls or something like that. Just select all of them and just smooth all of them at the same time. Yeah, that's important because, probably the biggest places we're going to have issues are where the two walls intersect, kind of like this. And so you want to smooth that out as much as possible. Yeah. Okay. And when I did this here, it was really fast because this model only has 2 vessels. But if you have more in your model, if you have more walls in your model, it's going to take longer. And so if you click smooth local and it seems like it's not doing anything, don't panic. That just means that it's working. It's working on it. Okay. Okay. Any other questions on this part right here? Okay. Okay, and so now that our model is smooth, we can go ahead and move on to the meshing. And so this is the part. This is probably going to be the biggest bottleneck, because if you can get past the meshing, and if your mesh can create, then you're going to be in really good shape. Okay. All right. So remember, the purpose of meshing is to break up our geometry here into lots of simpler shapes, so that we can perform our simulation. Right. And so let's go ahead and right-click on meshes right here, and then you're going to go down to this option right here for create mesh. And so let me go ahead and give it a name. Oh, first of all, you have to select the model. And so if you're doing this on yourself, you should have just one model here. Okay. Okay, so I'm going to give it a name test mesh, but you can call it whatever you want. Okay. Okay, so after you create your meshing object here, you should be able to, after you double click it, you should be able to open up the meshing settings here. Okay. And so there's a lot of settings that you can set with the mesh, but really the only one that's important is this one right here. Okay. And so what this setting does is that it sets the size of the elements. Okay. And so the smaller that you make your elements, the more elements you're going to have, and vice versa. Okay. And so usually what I like to do, if this is your first time meshing it, I like to click on this button for estimate. Okay. And what that estimate button is going to do is that it's going to look at your model, and then it's going to give you a decent edge size for that. Okay, that produces an okay mesh. Okay, so I clicked estimate, and for this model, I have 0.2007 for the mesh size. So let me go ahead and hit run mesher. Okay, run mesher is up here in the top right. And so it might take a while. And so this is another thing too, where your program's not frozen, probably. And so you just have to give it some time to run. Okay, and so that we have this bar down here to kind of show you that. Okay, so this mesh finished pretty quickly, and so when your mesh is finished, you should be able to see the mesh visually on your screen, and you're going to have a window here that shows up, which tells you your mesh statistics. Okay, and so the important line that you should see is the second line here for the number of elements. And so for this mesh, you can see I have about 258,000 elements. Okay, so that's a decent mesh. It's not bad by any means, but we can improve it a bit more. Okay, but just visually looking at it, this actually looks pretty decent because it's estimating the geometry pretty well. It's hugging it decently well, and the mesh density is actually not that bad either. So this is actually not a bad mesh. So I would actually feel okay running a simulation on this. For everyone that's following along, were you able to produce a mesh, or is it still running? Still running. Okay. Yeah. That can happen. Yeah. It can. Yeah, that can happen. And so you have to be careful a little bit too. So if you click estimate, and if your estimated value is like something really small, like 0.001 or something like that. Okay, then that's probably, yeah. Maybe I should have put some warning for that before we went for that. Because if you put a really small number there, then it's going to try to really fill it with elements. Because sometimes the estimate button doesn't really work that well. And so if it's coming up with something really small, then maybe we'll do you can try something else. But while that's running, I'll show you something interesting. Okay? Right. And so for this mesh here, with the mesh size of 0.2, we got about 258,000 elements. Okay. And so let's see what happens when I cut this in half. And so when I, instead of 0.2, let me do this with 0.1. Okay. right? And so generally what you expect, if the edge size is half right here, you might expect, your number of elements to double, right? And so if your elements are half the size, then it's going to take twice as many elements to fill the space, okay? And so let's see if that's the case, and let's see if my computer doesn't die as well, because this is a little bit expensive. Okay, but let me write out the number here so that you can see. And so before we had about 258,000 elements, okay, approximately. If you want to check the status of your mesh, SimVascular opens up this command window as well. And so if you click on the command window, you should be able to see this progress here. And so you should see iteration 1 out of 10, 7 out of 10, things like that. Okay. So for those of you who are meshing, are you able to see this? What iteration is it on?
I think it's on
6 million. Okay, all right. Hey, it finished though. That's good. Yeah, so you definitely probably not going to want to run a simulation with 6 million, but at least it meshed. And so the fact that it meshed is great. All right, and so we're done. Okay, so my computer did not blow up. Okay, and so let's look at the number of elements here compared to what we had before. Okay, and so if you read this number here, you can see that the number is about 2.1 million elements. Okay. And so by cutting the element size in half, we actually increase the number of elements by almost a factor of 10. Okay, and so so element size is not a linear thing, and so it ramps up really quickly. And so if you have a situation where you have like 6 million elements, maybe you might try doubling the element size. And so instead of what you have, maybe you do twice that. Okay, and then you're going to end up with a much more reasonable mesh. Yours just stopped responding. Yeah, that can happen. Yeah, just give it time. It might still be running in the background. And so this is definitely the bottleneck. And so I think last time when I had this project, I think I looked at maybe about 40% of the class just trying to help them get past the meshing part. And so the meshing is really fickle. And so I know some of you are coming from like my finite element class from before. And so meshing, and so if you used ANSYS before, you might think meshing is kind of an easy step, right? ANSYS makes meshing really simple, and so their mesher is actually really strong. And generally speaking, this mesher in SimVascular is actually pretty good too. But meshing in general is actually a really hard problem. And so there's a lot of things that can kind of trip up a mesher. And so a lot of it has to do with what the surface looks like, what the model looks like, and there's a lot of algorithmic, randomness in meshing as well. And so, meshing can be really fickle. And so, I think a lot of you will have a hard lesson in that when you're doing your final projects. Okay, so actually, let me course this up a bit, because I don't want to run a simulation on a 6 million mesh or 2 million mesh, excuse me. Is anyone doing the demo project, or is everyone trying to do it on their midterm project? Okay. No, that's good. That's good. Yeah. So I don't think everything here is not going to take super long, and so I think I'll try to save some time to try to go around and kind of help you guys individually. Okay. And so if you're still meshing right now, don't worry about it. But I did want to make sure I get through the whole tutorial today, so that we have that on video for people to look at. Okay. And so if you're still meshing, just kind of sit tight for a minute, just kind of, just watch along, and then I'll come around to you guys to help you out individually. Okay, so the next step is now that we have a mesh, or in theory, you have a mesh, in theory, the mesh exists in some space, okay? And so now we're going to set up the simulation. And so, we just go right along the tree here, okay? And so to create a new simulation job, you're gonna right click on simulations. You're gonna click on create simulation job right here, okay? And so just like before, you're gonna choose a model here, and it really is asking me to give a name. Okay. And so you're gonna have to give it a name there. Okay. And so after you create your simulation job, you can go ahead and double click it. And this is on the right here is where we're going to set all of our simulation parameters. Okay. All right, so the first thing you'll see is basic parameters here. And so here you're going to specify things like the blood viscosity and the blood density. And so these are already set, and so we don't have to worry about that. You're going to see a blank setting here for IC file. And so IC stands for initial condition. And so, if you're running the simulation based on another one, based on the results from another simulation, you can upload that here. But for now, we're just going to leave this blank. And so if you leave it blank, it's okay, because then SimVascular is just going to assume that you have basically zero pressure and almost zero velocity here. Okay. Okay, and so now we come to this part of the boundary conditions, which is the inlets and outlets. Okay, and so remember what we talked about on Tuesday, that when you run a CFD simulation, you have to specify what the inlet and outlet boundary conditions are. Okay, and so these basically specify how much flow is coming into your model and how much pressure is going to be there. Okay, and so I want you to look at the different caps of your model. Okay. And so, there's usually going to be at least one cap in your model. Some of you have more than one, which is going to be an inlet. Okay. And so for this particular model, this is the aorta. We know that, the heart is somewhere over here. Okay. And then blood's going to flow from the heart and it's going to go down the aortic tree. Okay. And so that means this cap right here is going to be one of our inlets. Okay. Okay, and so this cap right here is going to be an inlet. And so, first thing you're going to have to specify is the boundary condition type, right? And so for inlets, the way that we're going to specify that, if you click on this down arrow, you can see here we have 4 different options. Okay, and so inlets, what we're going to do is we're going to specify them as a prescribed velocity inlet. Okay, and so that's the first option here. So let's go ahead and click that, and then from that you should be able to have a prescribed velocity inlet for your cap. Okay. Okay, and so for prescribed velocities, we have to do something a little bit extra here. Okay, and so if you double click on this cap, okay, if you double click on the cap, it's going to bring up a new window right here. Okay, and so here is a window where you're going to specify, what the flow rate is from for this model. Okay, and so the way SimVascular does this is a little bit strange, but I'll kind of explain why it does this in a second. Okay. Because normally what you expect is that if you specify this cap here as a prescribed velocity, then what you can do here is just specify the velocity value here, right? And so let's say that we want a velocity of -100, okay? And so in other words, we want the flow to come into the model, right? So that's why we specify the flow to be negative. But for prescribed velocities, it's a little bit different. And so what you're gonna have to do is you're gonna have to double click on cap aorta, which is your inlet face, okay? And then you're going to need to specify what's called a flow rate file. Okay, so if you look at this setting right here, okay, you're going to need to upload a text file that specifies, what the flow waveform looks like in your model. Okay, and so if you downloaded the demo job, and in fact, actually, if you go to the course website, you'll see that I've uploaded this file here called steady.flow. Okay, and so what you're going to need to do is you're going to need to upload that into SimVascular. So you're going to click on these 3 arrows here. Okay. Right, and so you're going to go to the location where you downloaded steady.flow, and you're going to double click that, and then once you double click that, it's going to set the flow. Okay, and if you're curious what's in this file right here, it's a very simple text file. Okay. And so if you look into this file, you can see that it's just this. Okay, and so the way to read this file is that it's in 2 columns, and so this first column here is time. And the second column is flow, okay? And so what this describes basically is the flow that's going into your model as a function of time, okay? And so for this simulation, and the simulation that you're gonna run for your project, you're just gonna run a steady simulation. Okay? And so all that means is that your flow and your pressures are not gonna change with time. And so for a steady simulation, you really only need 2 time points. And so you can say that, our flow is going to be a constant -100 all throughout the simulation. Okay? And if you're curious about the units for the flow rate, they're in milliliters per second. Okay. All right, but of course, if you have an unsteady simulation, or if you want to have a flow waveform that looks more realistic, okay, so maybe you want one that looks like this, okay, which is the flow waveform that we talked about earlier in the class. earlier in the semester, then you can do that by uploading a different file. But for now, especially since this is your first simulation, we want to keep it as simple as possible. And so let's just run a steady simulation. Okay. All right, so let's go ahead and click OK. And so after you click OK, then it's going to specify the, you're going to get this, this tag right here to say that your inlet boundary conditions are assigned. Okay, so that's the inlet boundary condition. Now we're going to specify the outlet boundary conditions. Okay? And so for the outlets, for all the outlets in your model, you're going to specify them as resistance boundary conditions. Okay? And so remember, if you remember from our lump parameter unit, the resistance represents kind of the viscous, resistance to flow. Okay. And what that's going to do is that it's going to specify a relationship between flow and pressure at the outlets of your model. Okay. And so for the resistance boundary conditions, we have to specify their values, but we can do it in a special way. Okay. And so the way that we're going to do this, and this is actually talked about in the project specifications, is that you can specify that in terms of a total resistance. And so after you specify all of your caps as resistance outlets, what you're going to do is you're going to right click it, and you're going to click on this option here for split resistance. Okay. And so when you click split resistance, a new window is going to pop up, and it's going to ask you for two quantities. Okay? And so the first quantity it's going to ask you for is the total resistance. And so what that is the total kind of downstream resistance for this geometry. And then it's going to ask you for a Murray's law coefficient. But let's talk about how we compute this total resistance first. Okay, so if you go back to the project specifications, okay. Right, on page, what page is this? This is page 3, okay? On page 3, you're gonna see this formula right here for the vascular resistance of your model. Okay, so PVR stands for peripheral vascular resistance. And the way you're going to compute that is the target pressure in your model expressed in dynes per centimeter square, and then you're going to divide it by the inlet flow rate in milliliters per second. Okay. Okay. And so for a typical patient, okay, so first of all, for your models, you should look up and see what a typical blood pressure is. Okay. But for this model, I'm going to use a very standard pressure. Okay. And so for a typical person, their average blood pressure, the average blood pressure in a human body is about 90 millimeters of mercury. Okay, so that's kind of average blood pressure for a healthy person. Okay. Okay. And so the first thing we're going to need to do is we're going to need to take that pressure in millimeters of mercury and convert it to dyne per centimeter square. Okay. And so the conversion factor between those two is 1,333. Okay. And so to compute the average pressure in dyne per centimeter, you're going to take 90, okay, and you're going to multiply by 1,333. Okay. And so that's going to give you the pressure in your model in dyne per centimeter square. Okay. Right. And so if you're not sure what pressure to use for your model, you can definitely use 90 right here. Okay. So 90 is perfectly valid for a lot of models. But if you can, I want you to look up and see what a typical pressure is for that part of the body. Okay. Because some of you are doing pulmonary models and some of you are doing congenital heart disease models. And I will tell you that the pressures in those parts of the body are very, very different than this. Okay. And so for pulmonaries, you might see an average pressure of maybe about 15 instead of 90. And for congenital heart disease, it's even less. So it's about 10. And so, do a little bit of research, but you should be in those, roughly in those ballparks. Okay. And so this is our average pressure. Okay, I'm gonna go ahead and just round that up. And so that's just gonna be about 120,000. Okay. And so to get the total resistance, what we're gonna do is we're gonna take this and divide it by our inlet flow rate. And so the inlet flow rate, remember, that's the number that you specified in this flow file, right? And so in this particular model, we have a flow rate of 100. Okay. So I'm going to divide this by 100. And so we get a total resistance of about 1200. Okay. And so when we go back to SimVascular, we click this, we go click on split resistance. Okay. The total resistance here, I'm going to put just 1200. Okay. Any questions on that? Okay. Is anyone still meshing? it can happen. If you're still meshing, you might just want to close the program and just open it up, and then try again with the slightly larger mesh size. Yeah. Okay. And so that's the resistance. And so the next thing you're going to have to specify here is the Murray's law coefficient. Okay. And so if you remember, when we went over Murray's law, what we said was that we had this relationship, right? So we had r cubed plus is equal to r1 cubed plus r2 cubed. Okay. And so the Murray's law coefficient is actually the exponent values right here. Okay. And so you need to specify what that coefficient is, because depending on what part of the body that you're in, you might have different coefficients. Okay. So the default value here is 2, but you can go ahead and modify that based on the part of your body. And so for this one, I know that we're in the aorta. Oh, question?
Just to confirm, so Murray's law, it has to be cubed against the R3 and R1.
Yeah, it has to be cubed. Yeah. But it depends. And so for the aorta, we know that the Murray's law coefficient is about 2.3. Okay, so I'm going to do that there. But if you use 2 or if you use 3, that's usually fine. But if you want to be a little bit more specific, you can choose the appropriate Murray's law coefficient for that. Okay, so let me go ahead and hit OK. Let's see what's in the chat. Oh, yes, there you go. Yeah. And then after you split the resistance, you can see that your resistance boundary conditions here are specified now. Okay, and so if you notice, both of these resistance values are higher than what we initially specified. And so we initially specified our total resistance to be 1200. And so when you split them, you end up with higher values, and that's normal. Okay, so don't worry about that. All right, and so that's the boundary conditions. And so just to kind of summarize, when you're specifying your inlet boundary conditions, you want to specify it with the .flow file. And then for the outlets, you want to specify the resistance. Okay, and so the next thing we're going to specify is the wall boundary conditions. And so we can go ahead and click on wall properties here. Okay. And so here you can specify what kind of behavior that you want from the walls. And so if you click on this, there's 3 different options. And so you can either have rigid walls, you can have deformable walls with a constant material property, or you can have deformable walls with a variable material property. Okay. And so like we talked about last time, if you're interested in doing deformable wall simulations, you are certainly welcome to do so. But they can be very difficult to do. And so I would recommend at least at the very least for the first one that you do, you first do a rigid wall simulation, because that's going to be a lot more stable. Okay. And luckily that's going to be the default default setting for you. Okay. All right, and so now that we've specified, the inlet-outlet boundary conditions and the wall boundary conditions, we can now specify the solver parameters. Okay. All right, and so here's where we have to specify things like the time step size, the number of time steps, and the number of time steps between restarts, or in other words, how often that we want to save. Okay. Okay, so the first thing that you should specify here is the time step size, right? And so remember, this indicates, how much time there is in between the frames of your animation. Okay. And so, for this class, for most of your simulations, I think a time step size of 10 milliseconds is usually pretty good. Okay. And so the time step size that you should put there is 0.01 seconds. Okay. Okay. Next, we have to specify the number of time steps. Right? And so for a steady simulation like this, you usually don't have to run it for too long. And so, let's say that I want to run this for 1 second of simulation time. Okay. And so for time step size is 10 milliseconds, and I want it to eventually add up to 1 second. That means that the number of time steps that I have to specify is 100. Okay. Okay. All right, and then finally we have to specify how often that we want to save the results. And so for this one, you can choose almost anything. Don't put 1, because that's going to save too many results. But let me put 20 here just to make it a bit easier on my computer. Okay. Okay. And so there's those. And so the rest of these, there's a lot of other settings here, and unfortunately, this class is not long enough to kind of discuss, what each of these are. But I will tell you what my recommendations are for these. Okay. And so first of all, we have to go to setting 11 right here. Okay. So setting 11 here is the step construction. So right now the default value is 2. So usually for me, I like to crank this up a little bit. And so anything between 3 and 5 is usually good for me. So I'm going to go ahead and set this to 4. Okay. Right. Next, we have to specify these settings right here. Okay. And so what these settings are basically the linear solver tolerances that I talked to you about last time. Okay. So right now they're set to be a little bit lax. And so I like to tighten these up a little bit. And so what I like to do is that for each of these, from lines 23, 24, and 25, I like to set all of these to 0.01. Okay. Okay. And I think that should be it. Okay. And so for a steady simulation, all of these should work just fine. Okay. All right. And so now that our solver parameters are set, we're set to go ahead and create the simulation files. And so we're going to go to the last tab here for create files and run simulation. And so you're going to click on that. You're going to select the mesh that you made. Okay. And the last thing you're going to have to do here is click on create data files for simulation. Okay. And so note, if you haven't downloaded SimVascular yet, this is not going to work. And so when you click on this, it's going to send you, if it's going to give you an error message saying that SimVascular is not installed, or to make sure that you install it. But if you did have it installed and you click on this button, okay, it's going to give you a window like this to tell you that it's processing data and creating files. Okay. Right. And if everything runs okay, you're going to get this this message right here to say that your data files have been created. And then from here, you're good to go with running the simulation. Okay. All right. And so if you want to run this on your desktop, and so if you can definitely do that. And so if your mesh is about 250,000 elements or less, okay, then I would say that's actually pretty okay to run on your desktop just fine. Okay. And so for me, since I picked a fairly coarse mesh, I can go ahead and run the simulation. So let me go ahead and click run simulation. Okay. And then it's going to run the simulation for me. Okay. But if you have a much finer mesh, especially if your mesh is in the millions, I would definitely not recommend running it on here. Okay. And for your final project, I actually do want you to run a simulation on the cluster as well. And so, you can run a simulation first on your desktop just to do some initial testing. And so if everything is okay there, then what you can do is you can refine the mesh, and then you can run your simulation on a mesh that's like anywhere between 1 and 2 million. That's usually okay. And we'll do that on the cluster. Okay, and so that's it basically. And so that's a lot of the simulation. And so I'm going to kind of let this run, and I'll come back in maybe about 10 minutes. Let me go ahead. I'm going to go ahead and walk around the class a little bit for people that are kind of still struggling with the meshing. And then when we come back, I'll kind of show you kind of how to wrap things up, and I'll show you how to make accounts on the cluster. Okay, and so that's going to be the important thing. So I'll be back in about 10 minutes. And so if you have questions on Zoom, just go ahead and leave it in the chat, and then I'll come around to it after I talk to the people in person. Okay. Okay, so who's having trouble with the meshing still? Okay. You're just saying that's failed. Okay. All right. So let's try making it. Let's try refining it. Did you do smooth? Looks like it was. Okay. Okay. So let's try making it a little bit smaller. Let's try making it 0. Let's try 0. Let me see. So we have the so it's the other window that opens up. Oh, not this one. Yeah, the one that's kind of like the black box. Okay, let's try this. And so sometimes I've had success on checking this. So let's try on checking it. Let's try running it again. let's try this. Let's try the different algorithm. So let's try fast measurement. Usually it's a surface measurement. So let's try.
I have a chart this one. Oh my, plug it into my.
Let's try
The desktop. Normally I plug in my laptop, that's it.
Let me see your model looks okay.
Oh, failed to generate that.
Guessing it might be some of these areas like.
No, you want a smaller mesh. The smaller the meshes, the
Usually the
easier to take care of that.
You did too good a job in this. It's too accurate.
Yeah.
It's so accurate that it's having trouble measuring. Yeah, ANSYS, that's one beautiful thing about ANSYS, that the meshing is so well. Because this is kind of the typical experience that people have with meshing with other software outside.
You can try making mesh bigger.
So what happened with the test? Oh.
In 0.0.
Usually the volume meshes.
How old is that? It's not much better.
So usually when this happens, and that's the unfortunate thing too, is that the error messaging for the mesh is not useful at all. Oh, I said, this is what you want. Let's try. I think try for me off. Let me check on other people.
Yeah.
But yeah, just try to. Let's try this actually. So if you go to your model, so you can kind of mesh the different surfaces. Okay, and so what you can do here is that you see this button for mesh, and so you can try to remesh each individual face. So you click on this, click on estimate, click on remesh. This is one way to kind of narrow it down. If you try to mesh each individual, there might be one that kind of gives you that error, and so that's not that tells you what. Once you go through and kind of work with that.
Hey, Professor, didn't you say the smaller your mesh elements are, the more likely it is to not fail the longer it is?
Yes. Usually, but it's sometimes the mesher is a mysterious page. I guess having trouble with meshing.
Okay, so I chose the, I forgot what it's called, the one that's like your.
Oh yeah, congenital.
Yeah, right. And then, last time I asked you, because it has multiple, vessels out of the heart, and then once it gets to the heart, just get the right stop right there. So for the inlet, do I choose multiple?
Yes, yeah. And so let's talk about one.
Oh,
You
yeah.
do multiple inputs, you have to do this way you have to.
Okay, gotcha.
Have you got the mesh or is it still? Model is a little bit rough, so I think you might have to kind of smooth that a bit more. You might have, so when you do the constraint smoothing, you might have to change some of the other things, smoothing a bit more aggressive. Because I think it's yeah, I think if you kind of smooth that model, it should help a lot. I think the mesh, whenever you have basically a sharp angle on the surface, that's usually what's good. And so if you can kind of get rid of those, sometimes the smoothing is enough. Sometimes you have to kind of go back and rework your segmentations. And so what I always tell people is that the temptation is to try to make your vessels kind of fit the data as close as possible. But that doesn't mean anything if you can't mesh. So you go back and try to do the minutes of the segmentations to make the surface a bit smoother. Then just to try to get to mesh. That's usually, especially for a project, we don't have that. That's yeah, give that a try. I mean, if you try a bit more. That's definitely mesh.
What?
I mean, that mesh type is
Yeah.
But yeah, I would say for that. Yeah, unfortunately, I haven't had a chance to look at every one of the processes yet. But I can give you some feedback on that. We're just looking at smaller. Okay, but it hasn't failed yet. That's a good thing. If it gets a 10 out of 10, it depends how it. This is a test of ramp. Are you guys doing? Okay. Yeah, if it's too small, it's half an hour. Okay. Oh, so you got it. Yeah. Oh, perfect. Awesome. So. No, so you only want all of that. Because you're gonna mesh all together.
What? Mine looks a little weird.
Okay, that's okay. Yeah.
I know you're selling them.
Yeah. Oh, you did great. Looks like you got those. I mean, most people when it's get I think you probably got it. Yeah. Yeah. Okay.
Oh, I gotta give Hannah an update.
Okay. Is that the best?
So,
I said that.
What? I was taking notes. Oh, you're taking notes here? I'm just talking about cardiovascular.
That's the only measure. Yeah, I would say. The posture.
Yeah.
Okay. Okay, that's something that. Okay.
Yeah. So. It says it's done. Is that it?
Yeah, so actually, we're gonna do that next. So what you're gonna do next, and then this is already set, so you're gonna set this to be your starting simulation time. This is your stopping one. And then this increment is the, if you go back to your, I don't know why it doesn't do this automatically, but if you go back to your output parameters, this is the number exactly. So your start's gonna be 0, your end should be 100, and your increment is in between. I don't know why this doesn't set it automatically. It's right there. But yeah, that's your first simulation. So how many elements was it?
I tried to lower it, but then it didn't work. So
Okay.
then I had to make it higher again.
Okay.
Yeah. So I put it at 0.1 and it has, I think,
Well, 3 billion? It ran on your desktop. You're running on top. You got the most powerful laptop.
yeah, it was a GX 360.
All right. Yeah, so go ahead and try converting the results, and then I'll show you what they look like. Okay. Okay. All right. So we have about 8 minutes left, and so I want to make sure that we kind of close the loop today. So on my plan for Tuesday, I don't really have a plan for Tuesday, and so what I was hoping to do for Tuesday is to kind of just have a nice work session for this, because Because I know everyone's kind of in a different place with their project. Everyone kind of has a different project too. And so I think usually the best thing for me to do is just to kind of meet with everyone kind of individually. And so Tuesday, I don't have a plan, but if you can come to class on Tuesday and I can work with you on your model, that's what it's going to be for. Okay.
Wasn't you sent up a thing asking a poll saying what topic you want me to discuss?
Yeah.
You're not going to be discussing that on Tuesday?
I'm gonna record a video tomorrow for that.
Oh,
Yeah,
okay.
so it's gonna be a pre-recorded review video. So I'm gonna record it tomorrow. I'll send you guys the link, and then Tuesday we'll do a work session, and then Thursday we'll take the midterm. Yeah. Okay, and so before I wanted to go today, I did want to show you what the simulation results look like. And so unfortunately, you can't view the simulation results within SimVascular, which is something I've complained about, but the developers are tired of hearing from me. So, but what you need to do is you need to convert your files. And so, okay, my simulation is still running, and so I can't do this yet. But if you ran your simulation on your desktop, what you should see when you go to convert results is that this directory here should be populated. Okay, and so this should have a folder which has all your simulation results. And so what you're going to do from here is you need to specify the starting time step. And so for most people, your starting time step is going to be 0 because you're going to start at the beginning. Okay. Your stop time step is going to be whatever you specify to be the maximum here. And so in this case, we set the number of time steps to be 100. And so my stop's going to be there. Okay. And then you also need to specify the increment. And so the increment is going to be the number of time steps between restarts. Okay. Okay. And so you're going to hit that. And you're going to hit convert. Okay. And then it's probably going to take maybe a minute or two to convert your results, depending on how big your mesh is. And then from there, you should have the results. And so to view the results, let me get this annoying number out of the way. Okay. And so to view the results, you're going to go to your project folder on the Windows Explorer. Okay. You're going to go to the simulations folder, and then you're going to go to the name of your simulation job. Okay. So mine's not done yet, but this one already has a completed job. Okay. And so you're gonna go to demo job, and if you converted your results successfully, then you should have a folder here called here demo job -converted -results. Okay. And so if you open that folder, you should see a list of files right here. Okay. And what these files are, these are called VTP and VTU files. Right? And so the VT stands for visual tool, and the P and the U, I forgot what they mean. And so, but basically these are special files. So these are basically 3D model files. So you can almost think of it as kind of like augmented CAD files almost, okay? And so to view these files, we're actually going to need a specialized software. And so, probably, all of you don't have this on your computer, but the software is called ParaView, okay? So ParaView is a free software, and so you don't have to pay for anything, okay? And what it is, it's basically a really nice kind of 3-dimensional viewer software. Okay, so I love ParaView because it's relatively lightweight. And if I want to view like a CAD model, like a SolidWorks model, or like a mesh, you can just go to ParaView, and it's a lot more lightweight than using like SolidWorks or something. Okay? So I think ParaView is a great software, but I'm a big fan, but but other people have other opinions as well. Okay, and so to view the results, you're going to open up ParaView. Okay. I think the easiest way is to just click and drag. And so you open up your window, you click on the file that you want to view, you just drag it into ParaView, okay? And then from there, you're going to click on this button here called Apply, okay? And you can see here your model. And then from there, you're going to go to this drop-down menu right here, and you're going to select the result that you want to see, okay? And so let's say that we want to view the average pressure, okay? And so there is the average pressure in this model. So I actually don't know what's up with this model. This model results are a little bit weird, because normally you would expect the higher pressure to be at the inlet over here. But for some reason, the maximum pressure is down here, and I'm not really sure why. And these are the results that are published on the official website. And so it's a little bit concerning that they're publishing results that look kind of weird. Okay. All right, and so that's it. And so once you have your simulation results, you can view it in ParaView. And then what I like to do from here is I like to screenshot. And so you can either use the snippet tool in Windows. I know there's a lot of hate for the snippet tool, but I'm okay with the snippet tool. Or you can use the screenshot feature that's here in ParaView. Okay, and so then you can put those into your report. Last thing before we close today, I want to show you how to make accounts on the gateway just so that we can be ready to go, okay? And so if you open up a web browser, right, you open up a new one, you're gonna go to the site called gateway.simvascular.org, okay? Okay, and so you're gonna go to this website right here, and you should be greeted with the title of the website, which is SimVascular Supercomputing Gateway, okay? And so in order to use this gateway, you're gonna need to make an account. And so you're gonna click on create account here, okay? And the nice thing about this gateway is that because it's sponsored by NSF, you know, if you're part of an academic institution, you already kind of have an account. You just kind of have to register with the gateway, okay? And so luckily for us, you know, you guys are all students of Cal State Fullerton, and so you have an official Cal State Fullerton account email. And so what you're going to do is you're going to click on this button right here for sign in with existing institution credentials. Okay. And then and mine kind of automatically takes me to Fullerton because I've done this before. But I think the first time you click it, it's going to ask you what organization or what institution that you're part of. Okay. And so Cal State Fullerton is part of that list. And so after you click on that, it should take you to the usual kind of Cal State Fullerton login. And then you can enter your username and password and you click login. Okay. And then it'll automatically create an account for you. Okay. The thing with the gateway is that, you know, it's still, you know, so this is actually one of my pet projects. And so I've been working on this for a couple of years now. And so it's still kind of in its infancy. And so I don't just let anyone kind of run a simulation on it because I know that trolls exist. I know, and trolls are out there that will just drain my entire cluster. And so what I do is that once you create an account, I have to approve you just to make sure that you can, you know, just to make sure that you're a real person. And so after you create an account, then I have to go in and approve it. So you're not going to be able to run a simulation right away. But over the next week or so, I'm going to be regularly checking for everyone with a Cal State Fullerton email and just kind of approving you to run simulations. So by the end of next week, you should be able to use the cluster just well. But the first thing you have to do is to make an account just so that I can approve it. Okay. Okay, and so that's it for the workshop for today. And so we kind of went through the whole process. And so I know people are at different stages depending on where their mesh is. But on Tuesday, we'll keep working on this. And so if you can bring your laptop on Tuesday, if you want to keep working on it over the weekend, and then on Tuesday, we can just keep going. Because I think, you know, what ends up happening with this class once we're at this stage, you know, I end up kind of having to meet with almost everyone in the class. So I want to dedicate some class time for doing that. And so if you were able to get through the entire thing today, that's great. Then you can kind of take Tuesday off. But you know, if you need my help with anything, you know, just come prepared on Tuesday, and you know, I'll be going around helping people. All right. Any final questions before we wrap it up for today?
For the exam, just notice memorizing this data can study guide.
Yeah. Remember, you have a cheat sheet too, and so you can write whatever you want on the cheat sheet as well in terms of conceptual knowledge.
They're pretty like word for word with some study guide, right?
I try to, yeah. So I mean, I don't like throwing. I never like getting curveballs on exams, and so I don't do that myself too. Yeah. Okay. All right, so that's it for today. So thank you guys for coming today. Thank you guys for the ones that were following along. Hope you guys have a good weekend. If you have questions on the exam, you know, please let me know, and I'll see you guys next week. Thanks, guys. Yeah. Oh, really?
It's still trying to run.
Did any of them work or I'm still trying. Okay. I see. Wait, is this the whole thing or is this just individual? Okay. Oh, 1A. Okay. It's still stuck. Okay. Okay. Yeah. It looks like it's. Oh. Yeah, I'm not sure how. Because there's usually. Your RAM is getting yeah. Oh. That's probably why. Yeah, these laptops were not designed. Let's try this. So can you send me your model? Let me try meshing on my desktop because I would have a model too. So that should be a little more successful.
I have my
Okay. Yeah, I think that's kind of what's happening. The good thing is that it hasn't failed. And so if it hasn't failed, that means it must still be working. But so I will say that for SimVascular, it's you know, it was designed by the way
underpaid grad students. So there's never this all. What can happen sometimes is the mesh fails. And then you can actually like access your until you close it out. Sometimes the best thing is to do software. Okay. Yeah, and if you're having trouble, we can continue working on
Process. So that last week, I also kind of planned it to be. So I have two things planned for that week, and so for the Tuesday, I was going to have just another work day, just because that's our last week of class, and so I want to spend that day helping people with their projects, getting people up to speed with the simulation, and then Thursday I have a guest speaker, and so yeah, it's it's not going to be anything more important. So after the exam, we're basically focusing almost entirely on the project, and so if you're making good projects on the project, then then there's nothing you're really going to miss. Yeah. Yep. Mm-hmm. What's up?
I was just like gonna ask if you're using any advice besides running the mesh.
Yeah, so if the mesh size, so typically what happens is that if you estimate mesh size is so small, and it's detecting like a very small feature. Remember we talked about fine balance that whenever you have a really small feature, the mesh really small features. This is kind of the manifestation of it. And so sometimes what can happen is that if you smooth, you can get rid of those small features. But sometimes you just kind of have to get rid of them. So I would try to do a scan on your model and try to look and see if there's any small features. Another thing you can do to debug it is that usually it's just in one region of the model. You can do that too, but then what you can also do is that you create the model. Normally you select every segmentation. So try just doing one at a time. So just doing this one, then meshing it, this one, and then a second one. Usually that'll help you kind of narrow down the errors. Because usually it's just one or two vessels that are giving you trouble. And you might have to go back and modify the segmentation. There's a lot of things. So that's why Tuesday we're gonna have another. Yeah. Yeah, just give your laptop a break for today.